Hey everyone, welcome to homework 3.17. So today we looked at compound interest over intervals of time. So I'm going to go over that just a little bit and a few reminders. All right, so we have the population of a city in 2010 was 50,000 and it grows by 5% each year. Write a function which models the population of city T years after 2010. So here we have each year and we're talking about years. So we don't need to do anything specific to this. We're talking about what happens after a certain number of years. And so we're going to then multiply this by 1.05 because it is increasing by 5%, and we are talking about T years after 2010. So in 2017, we would have 50,000 times 1.05 to the power of 7, because that is 7 years after the initial date of 2010. So 50,000 times 1.05 to the power of 7 gives us 70,355 and 0.02. So around 70,355. We're not going to count decimals of people. What will the population be in 2020? What about in 2030? So in 2020, that is 10 years later. And then in 2030, that would be 20 years later. So I'll let you go ahead and do the calculation there to find the answer to that. So here and here. By what factor does the population grow between 2010 and 2020? And what about 2020 and 2030? So in thinking about how much is it growing between those times, right? What factor does it grow? It's growing by 1.05 to the power of 10 and 1.05 to the power of 20. So we want to think about how much it is growing by during those periods of time. But to do that, we need to consider the change that has happened since the beginning. So we would think about this whole amount in 2020 divided by the amount we have in 2010, which was just 50,000. In this case, it would be the amount, so that original amount, divided by what it was in 2020, right? So 2030 divided by what it was in 2020. And so when you do that, let's go ahead and do that here. 50,000 times 1.05 to the power of 10 divided by, oops, gotta go back. Let's try that again. Unless I made a mistake, I forgot to use the over arrow. 1.05 to the power of 10. Nope. Having all kinds of issues here. Okay. To the power of 10 divided by 50,000, which was our original amount in 2010, will give us 1.63, we'll round to. All right, so it's increasing by approximately that amount there over those 10 years. And then we are looking at 50,000. Actually, let's go ahead and do parentheses so we don't. 50,000 times 1.05 to the power of 20 divided by 50,000. I think I have too many zeros there. Go 1.05 to the power of 10. All right. So when we do this, we also get 1.63, right? So it's around 1.63 is the factor that we are multiplying by for those, 10 years that we are looking at. All right. So let's take a look now at our next piece here. A person charges $100 to a credit card with a 24% nominal annual interest rate. So this is what we're getting into when we talk today. Remember, this is the named interest rate, right? It's not the actual interest that we're going to get. It's what they're telling us we're going to get. Assuming no other charges or payments are made, find the balance on the card in dollars after 1 year if interest is calculated annually, every 6 months, every 3 months, monthly, or daily. Whew, okay. So if it's annually, it's 100 times 1.24 to the power of 1, right? It's happening one time, where I do have a 24% for that year. So we have $100 times 1.24, which is going to be 124. Now here, every 6 months now, I'm doing 100 times. Now 24% divided by 2, because every 6 months means 2 times, then it's going to be 12%. So 1.12 to the power of 2, because I'm doing it again 2 times. So 100 times 1.12 to the power of 2 gives us 125.44. So remember, that makes sense because it's increasing from that amount for just happening 1 year. If we're calculating that interest in over a different period of time, the number of times that we're doing that, we need to divide our percent into that number of times, or by that number of times rather, and then raise it to that power. So every 3 months means that now it's happening 4 times. That's quarterly. So 100 times 24 divided by 4 is 6. So this would be 6%, 1.06. But instead of 2 now, I'm doing it 4 times, so to the 4th power. And we should see a number that's slightly larger, right, if we did this correctly. And that's a good way for you to check, does that make sense? And I get 126.25. That looks great. It's just a little bit bigger. Now monthly, 100 times 1 point. Now monthly means I'm doing it 12 times. So 24% divided by 12 times means 2%, right, each month. And so, and then I have to raise it to the power of 12 because it's happening each month. So 100 times 1.02 to the power of 12 gives me 126.82. So again, that is a little bit more than the one that we did before it, which means that that looks like it makes sense. All right. So then this last piece is asking us to calculate it daily. So if we are doing 100 times 1 point, now this time we are dividing it by, daily means 365 times, because that's how many days are in a year. So 24% divided by 365 gives us 0.065%, which means the decimal is going to even be more than that. So we would have to move this decimal over 2 places. So we would have 1, 2, 1, 2. So I should have 1, 2, 3 zeros, 6, 6. We'll say, we'll round it up just a little bit, to the power of 365, because we're doing that every single day. All right, so 100 times 1.00066 to the power of 365 gives us 127.23 approximately, right? 6 honestly might have been a little bit big because our number was 65. Let's do a little bit more decimals. 1.000657534. We'll just do it a little bit longer. To the power of 365, we get 127.11. That seems to be a little bit better. It's a little bit closer to what I was expecting. So say an 11 cents. All right, this again, when you round, what happens is you get a number that's also slightly bigger or slightly smaller than the actual number. So if we put in this whole number here of 657534, etc., we'll get a more accurate representation of number. All right, number 3, a couple has $5,000 to invest and has to choose between 3 investment options. Option A is 2.25% interest applied each quarter, so 4 times. Option B is 3% interest applied every 4 months, so that would be 3 times. And 4.5% interest applied twice a year, so this would be 2 times. If they plan on no deposits and no withdrawals for 5 years, which option would give them the largest balance after 5 years? So now we're talking about 5 years happening. Now, I do want to mention that we are looking at these percents here being applied each quarter. So this isn't the nominal interest. This is what percent is being applied each quarter. So our mathematical representation for A would be 5,000 times 1.0225. Okay, and that's because 2.25% is 2.25%. We need to move that decimal over 2, and so it'd be 0.0225. And then here, if we are doing this 4 times, but we're doing it for 5 years, we need to multiply by 5. So we get 5,000 times 1.0225 to the 20th power, right? Because if we do it for 5 years, that's how long that's going to be. All right, plan B would be 5,000 times 1.03% interest, but this time we're only doing it 3 times, and we're all still doing it for 5 years. So we're going to need to multiply by that 5. And so that would be to the 15th power. And then option C, which is 500 times 1.045, 4.5 interest, right? 4.5%, 4.5%. Move that decimal over 2. And this is twice a year, so to the power of 2, but again for 5 years. So let's go ahead and see, that would be 5,000, I wrote 500, so 5,000 times 1.045 to the 10th power. So then you're going to go ahead and calculate each of those and see which one is going to yield the best deal for you. So will it be the one with smaller interest and being compounded more often, or higher interest and compounded less often? So you all, I'm going to highlight this because you all need to actually calculate that and decide which account is going to be best, A, B, or C. And I'll be looking for that on your homework tomorrow to know that you did that part. All right, number 4 says that Elena has 6% interest applied semi-annually 2 times a year, and it is the same as 1% interest applied every month. She reasons that they are the same because they are both a 12% nominal annual interest rate. Is Elena correct that these two situations both offer a 12% nominal annual interest rate? So yes, that is the definition. Oops. Because 6% interest would mean that for a whole year we would have 12% nominal interest rate. 1% each month would still be 12% nominal interest rate. So they both have the same nominal annual interest rate, but is it correct that the two situations pay the same amount of interest? No, because we would be compounding the 1% interest more frequently. So no, because the 1% each month is compounded more often. All right. And then if you want to prove that, right, let me just show you as an example. Let's say we have $100 and we invest it twice a year at 6% each, right? So 2 times a year. And let's say we have $100 and we invest it at 1% for each month, so 12 times, right? We have 100 times 1.06 squared versus 100 times 1.01 to the 12th power, right? This one is going to be a little bit more. So 100 is a pretty small amount, and the percent's pretty small too, but it's still going to be a little bit more if we compound it more frequently. All right. Number 5, a bank pays 8% nominal annual interest compounded at the end of each month. An account starts with $600 and no further withdrawals or deposits are made. What is the monthly interest rate? All right, so 8% nominal annual interest compounded at the end of each month. So 8% is being now broken up into, because that's the nominal interest, 8% is going to be broken up into 12 months. So 8 divided by 12 gives us 0.6 0.66666%. So as a decimal, the monthly interest rate, sorry about that. So if you wanted to, you could also have written this as a decimal as 0.0066666, right? Moving that decimal over 2 points would also be fine. Sorry, you all, that this is so disjointed because I have now been interrupted multiple times. But anyway, the expression for the account balance would be 600, that's our starting amount, times 1.0066666. You can go on however many times you want, to the power of 12. If you wanted to also write this without all of those decimals, you can write it as 600 times 1 plus, right, because we're adding that 1, to 0.08 divided by 12. That's that 8% divided by 12. That's what you did up here, right? 8 divided by 12. So these are equivalent expressions, but if you put this in the calculator, you're going to get a more precise answer than you will with this one, just because those 6 will continue forever and we stopped. All right, the effective annual interest rate. So the effective annual interest rate is when we take this, not that, that's incorrect, 66666, and do to the power of 12, and then we look at that decimal. So let's do that. We'll actually use this one right here. So 1 plus 0.08 divided by 12 equals, and then we're going to do this to the power of 12, gives us 1.082, right? So then when we do that, we have 1.082999. The percent I'm looking here is 8.29%, or maybe 8.3% if you wanted to round up. It says, what is write an expression for the account balance in dollars after T years? So our expression is 600 times, and again, it can be equivalent to this, or you can do it however you like, to the power of 12 times T, that 12 representing the months and the T representing however many years we decide to continue doing this. Again, this part right here, if you rounded those 6's, could be 1.00666667, something like that. Instead, this will give us a more precise answer if we enter that into the calculator. All right, let's take a look at number 6. At the end of the year, 10% interest is charged on a $500 loan. This interest applies to any unpaid balance on the loan, including previous interest. Select all the expressions that represent the loan balance after 2 years if no balance payments are made. All right, so this is yearly, annually, no month. We don't need to do any special division or anything. We have $500. And then we are going to be taking adding that 10% interest every time. So when we're adding that 10% interest, we could be multiplying by 1.1, right? So if we were to write that, it would be, and then to the power of 2, right? Because it's going to be for 2 years. So we can see that here is written as this. We can also see that written this way. In this case, we're just adding decimals to that, so that doesn't really make sense. In this case, we are multiplying 2 times 10% of 500, but that's not accurate because we would be taking that interest on top of the owed amount after the first year. Okay, so B and D are your best answer options. So let's take a look at E. Now E would also work because when we multiply the first 1.1, so 500 times 1.1, we get 550. So after the first year, it increases by $50, and it would be 550. And then we can also then multiply again by that 1.1, 110%. And that one also is represented. It's written a little bit differently, but it works. Number 7 says, here is a graph of the function. Suppose g is the function given by g of x is 50 times 1.5x. Will the graph of g meet the graph of f for any positive value of x? Explain how you know. So if we're looking at g of x, it would be starting lower. And notice here that it is growing slower, which means that the graph would come out this way. And so it would not go up past the other graph. So no, because it is exponentially growing slower, right, at a slower rate. All right, number 8 says a bank account has an annual interest rate of 12% and an initial balance of $800. Any earned interest is added to the account, but no other deposits or withdrawals are made. Write an expression for the account balance. After 5 years, if interest is compounded n times per year. All right, so if we have 800 and then it is compounded multiple times in 1 year, then we are going to be looking at multiplying that 12% divided by that number of times. So 800 times 1 plus n, 0.12 divided by n to the nth power. And then if it's 5 years times 5, okay, depending on how many times it's compounded. After t years, if interest is compounded n times per year. So 800 times 1 plus, again, 0.12, that 12% divided by the number of times we do it, to the power of n times t. After t years with an initial deposit of p dollars. So instead of $800, we have p dollars, again, 1 plus, and an annual interest percent rate of r divided by n to the power of n times t. All right, so this is the principal amount, the initial amount. This would give us our factor, that's 1 plus the rate divided by the number of times we're compounding it, all to the power of the number of times we're compounding it times the number of years. Okay, because if we compound it 3 times a year for 3 years, that's 9 times. If we compound it 5 times a year for 3 years, that's 15 times. All right? That's it for your homework today. If you have any questions, feel free to reach out. Again, sorry for all of the interruptions. Happy homeworking and see you tomorrow. Your code word for today is highlighter. Again, it's highlighter. If you have any questions about the classwork, which I didn't have time to go over today, you can feel free to text me and check your answers with me.